So today we will discuss the recovery of non-relativistic limit from the Klein-Gordon equation, the relativistic equation what we have learned for wave functions. So we know that now we have to deal with the Schrodinger, instead of Schrodinger equation, the Klein-Gordon equation for relativistic particles. So if I just can go back to the slide where we had written the Klein-Gordon equation is this one. So here we see that this is the equation which really governs particles moving at any speed. However, we have seen and we have examples, lab verifications of things. The Schrodinger equation is not too bad. That means if I am looking at particles which are not moving with very high velocities, for them effectively we can approximate the quantum evolution by Schrodinger equation. So how do we recover that? Schrodinger equation is also recoverable at low speeds limit from the Klein-Gordon equation. So one thing is that when I want to go to non-relativistic limit, there are essential statement is that V upon C is a ignorably small quantity. When I take V upon C tending to zero limit, that means there is no velocity whatsoever compared to C. So in that sense, the equation will be free of C. They should not, we know in the Schrodinger equation, there is no appearance of speed of light C. So one way of doing that would be taking this V upon C tending to zero limit. That means beta goes to zero, the special relativity parameter beta goes to zero. In this process, wherever I see V upon C in the Schrodinger equation, in the Klein-Gordon equation, I can put it to zero. But in quantum mechanics, we do not pose problems in terms of V, rather than we have a P upon C. Momentum upon MC, let us say. Whenever P upon MC is zero, then also we can recover the non-relativistic limit. In quantum mechanics, this will become operator. So momentum operator upon MC is supposed to be very small. But if I do that, that means that I have to throw away the whole terms which are like P upon MC. Remember, the Klein-Gordon equation which we had written down is a manifestation of the statement that E square upon C square minus P square upon P square C square is equal to M naught square C square. Okay, so sorry, so there should not be C square here, so there is just P square. Now if this is the case, if I divide everything by M naught square C square, or the rest mass, so in that case I will get here 1, and here I will get M naught square C square, and here I'll get M naught square C to the power 4. If I take this quantity to 0, that is a valid non-relativistic limit, but that will erase out all the momentum. So momentum is not appearing in the equation afterwards. So there are all spatial derivative will go away if I employ this technique, that I have to get this quantity down to 0. For a finite C, speed of light is finite, so only thing is that P upon MC can approach 0 is only through if momentum goes to 0 limit. That means we will be talking about non-dynamical particles which are just located at a point, not have any other distribution in space. That would not be very beneficial, because we want to know, Schrodinger equation also talks about probability of particles of being here, there, moving with certain velocity, momentum expectations and whatnot. So I do not want P going to 0. So what should I do? The other way would be to take C tending to infinity limit. C tending to infinity limit is also a non-relativistic limit. That means any speed, finite speed, is practically ignorably small compared to the speed of light. This is not really infinity, but V upon C is ignorably small quantity. This is a dimensionless number. So what it tells is that it is very large number, and V upon C can be ignorably small, and I do not have to throw away the P tending to 0. I do not have to take. I can maintain P, and whenever I see a appearance of C, I will compare with terms wherever C are present or not, and I will see that C tending to infinity limit, what will happen. So one thing which will happen is, in the relation which we wrote down, E square upon C square minus vector P square was supposed to be M naught square C square. So the right hand side is going to become very large. That is very high rest momentum or rest energy. rest energy or rest momentum is very high. That means compared to its rest mass, you are not moving at sufficiently fast velocity. So this is non-relativistic limit is also high rest energy limit or rest momentum limit. That means due to your inertia, the momentum developed, inertia meaning energy due to m naught square, m naught c square would be the rest mass energy that is much dominant over other forms of energy like kinetic or potential. So that is the limit we will try to use without sending momentum to zero, and then try to recover the non-relativistic limit out of the Schrodinger equation or out of the Klein-Gordon equation. So let us try to do that. When I write the stationary state psi xt, we have seen that previously it should be some phi x times e to the power I e t upon h bar minus I e t upon h bar. That is what the stationary limit we have discussed before as well. Now in this E, there are two terms hiding. E is the square root of p square c square plus m naught square c4. So there is a, if m c square is very large compared to pc, I can pull out this m square c4 out. Then I will have a m c square, and under root I will have a 1 plus p square upon c square and m square c4. This is what we had done for kinetic energy, if you remember as well, that we went to a frame where this ratio was very small. So that is to say, the energy can be written as a Taylor expansion of this quantity as we had done, mc square plus times 1 plus p square c square m square c4 with a power half plus higher powers, as we have seen for kinetic energy expansion. So what we can do, we can separate out a rest mass energy factor mc square times 1 from the total energy, and I can pull it out in the exponential. So this e to the power minus I e t upon h bar is made from rest mass energy plus other higher order terms which depends upon the ratio p upon pc upon mc kind of things. So this mc square kind of thing. So this kind of expansion we can do, and I can pull out this, saying that rest mass energy is very high. So I can have a Taylor expansion and then I can pull out this thing. This is just simple mathematical trickery which I have pulled out. So therefore I can choose to write my wave function in terms of exponential which solely depends on the rest mass energy coming from this mc square and the 1 in the Taylor expansion, and all other things I keep along with phi x and define it a new phi x of t. So this is just rest mass pulling out, which I can do mathematically. There is no problem with that. Then I do the first derivative. I will get a d phi upon dt when the derivative will hit this and the exponential back. And when the derivative hits the exponential, I will get a minus I phi mc square, because there is a t linearly proportional to the t term in the exponential and there is a phi outside. So I will get mc square by h bar with a minus iota here and the exponential back. Similarly, if I take the double derivative, you will get this kind of term. First the double derivative will hit this term and leave the exponential around, then the double derivative hit the exponential and leave the first term around. So this is what you will get. You can simplify that. You will get terms like d2 phi dt upon dt square minus twice iota upon h bar mc square d phi upon dt and minus m square c4 divided by h square times phi. So the double derivative of this splitting will give you this rise to this kind of terms. Now if I want to do double derivative with respect to x, in this kind of a splitting, x is only appearing in this phi. In this second part of the exponential, there is no x. So d2 psi upon dx square will just hit the phi part, and I will have a double derivative of phi with respect to x. And similarly for y, and similarly for z as well. So I would have three kinds of term for spatial derivatives, all hitting the derivatives, all the derivatives hitting the phi. In temporal part, the derivatives will hit phi twice, one times phi and one times the exponential, and twice the exponential, meaning double derivative on this product function can have splitting that double derivative solely x on this, double derivative solely x on exponential, or double derivative splits upon one derivative on phi and one derivative on exponential. And then we can put all these terms back into the Schrodinger equation. From the spatial derivatives, I will just generate the Laplacian part of phi with exponential out. so that I can write like Laplacian times exponential out. From the temporal derivative, I will get all these terms. And remember, in Klein-Gordon equation also there is a rest mass and a rest momentum m square c square upon h square term, which you can see gets exactly cancelled from this term. There is a minus sign here, but remember double derivative appears with a minus 1 over c square. So therefore it will turn things into a plus, and therefore this will exactly cancel the rest mass term. So I will be left with the first term, the second term, third term goes out, the fourth term which survives, and this exponential. So ultimately I have these three terms surviving times the exponential is equal to 0. Obviously exponential cannot hit value 0. So that means the terms in the bracket should be equal to 0. Alright. Now look at the structure. I have this kind of thing where a double derivative of phi is appearing, a single derivative of phi is appearing, and the Laplacian of phi is appearing. Now in the limit, when the term which is double derivative of phi is very small compared to the single derivative term as well as the Laplacian term. So suppose this is happening, that this is the weakest of them all. That means h bar magnitude wise, forget about iota or signature, magnitude wise iota h bar m times d phi upon dt term should be much greater than the d2 phi upon dt square term. Okay, if that happens in the temporal part, if there are two terms, I can say that this is much greater than that, so I can maintain this and throw away this away. So therefore if I do that, I will be left only with one term as temporal derivative, which is d phi upon dt. We have chosen that the second term, the first term is much weaker than the second term, and in that case you will see the remaining two terms exactly give rise to the Schrodinger equation. So in the limit, when the double derivative of phi is much smaller than the term compared to the single derivative of phi. Remember, phi was what? Phi was the rest mass independent part. Rest mass energy was coming in the exponential. I have pulled out the rest mass energy. So therefore, rest mass energy independent part is the phi. That phi's double derivative is much weaker than its single derivative. In that limit, I get the equation which governs the phi, which is rest mass independent part, is the Schrodinger equation. All right. So let us look at in what limit the Schrodinger equation has emerged. As we saw, first derivative is much stronger compared to the second derivative, or second derivative is much weaker than the first derivative. If you arrange things properly, you will see the coefficient multiplying the first derivative is exactly h bar mc square. That means mc square, rest mass energy, has to be much greater than the double derivative divided by the single derivative times h bar. So sorry, this h bar should have been in the denominator actually. All right, so that tells me that the rest mass energy has to be much greater than the log derivative of phi dot. Phi dot is the temporal derivative of the wave functions, that part which does not contain the rest mass energy. It has some time profile, it has some time derivative. That time derivative should not change much faster, meaning the time phi dot should remain practically constant, meaning it should not be very high. So that means double derivative is much weaker than the single derivative, and the scale to compare how small is small, that the ratio should not come close to the rest mass energy. So there should not be rapid variations in time for the phi dot. Phi dot should practically smoothly, very slowly evolve in time, not very fast. Okay. So if the rest mass energy is high and variation in the time for the time variation, that meaning variation in phi dot, del t of phi dot should be much smaller. For that part of the wave function which is not containing the rest mass energy, in that limit, that function phi dot or phi behaves as the part which is Schrodinger equation. So the part of, you can see that the probability, if I used to believe in non-relativistic probability density, which we will see in the couple of minutes, if I take psi mod square, it is also equal to phi mod square, because exponential part of rest mass energy is just a phase. So effectively, you can say that in the non-relativistic limit where rest mass energy is too high, then the actual wave function is the Schrodinger wave functions up to a phase which is very high, which we can ignore as well, because effectively there is no new information the phase is bringing about. So this is the high rest mass energy, not zero momentum case. The high rest mass energy of the wave function is the limit in which you do get Schrodinger equation back. Okay. So that is the understanding how to get from the Klein-Gordon equation the Schrodinger equation back. Fine. So once we have understanding how to get the Schrodinger equation and other things, let us look at the definitions of probability densities, the probability current, and all other things which we have learned for Schrodinger equation. Now we want to see the analog in relativistic setting and want to see whether again it is possible to recover the usual probability density, and if there is any need to modify the definitions of probability and probability densities and probability currents in the relativistic domain. So again, we start with the Klein-Gordon equation, which is this. You can see that the box operator over here is made up from the double derivatives of space and time, all coming with real coefficients. And then there is a rest momentum m square c square divided by h bar square acting on psi. So all these quantities inside the bracket, all the operators which are acting on psi are real quantities. They are meaning real derivatives. Now if I take the star of this complex conjugate of the whole equation, nothing will happen to the box because it is made up of real quantities. Nothing will happen to the rest momentum as well because it is also made up of real quantities. The only thing that will change will be psi star. Psi will go to psi star under complex conjugation. So that means psi and psi star both satisfy the Klein-Gordon equation. Remember, in the Schrodinger picture as well, psi and psi star were also the solution of the Schrodinger equation with a potential phase difference of I pi. There is a minus sign which would come about due to flip of iota h bar. And since overall phase is not a matter of concern, then psi and psi star is also a solution of the wave equation, of the Schrodinger wave equation. Relativistic setting also we are getting the similar kind of thing, that both psi and psi star are satisfying the wave equation. So now exactly like we proceed for deriving the probability current equation, we just take multiplication of the first equation with psi star and multiply psi with the second equation, and then we subtract them out. So I would have a psi star box psi minus psi star m square c square h square psi, and then the reversed role of that psi and box of psi star minus psi m square c square h square psi star. So while the boxes will have psi star and psi flipped across them, similarly m square c square h square will have psi star and psi in the first equation on the left and the right respectively, while in the lower equation psi and psi star are coming on the opposite sides. But since this is a constant kind of thing, m square c square h square is not a real-time non-trivial operator. So therefore this can come out and psi star together can give rise to psi mod square. The box cannot do that because box has derivatives which have to act on psi, or the box over here has to act on psi star first. These things can do that because they are nothing to do derivative operation, they are just multiplication operators. So they can come to the left and both the terms will then become the mass term c square h square times psi mod square, and under subtraction they will exactly cancel out. So I will be left with a psi star with a box of psi minus psi times box of psi star. Okay, so let us open the boxes for both the terms and collect all the temporal derivatives and all the spatial derivatives. So if I collect all the temporal derivatives on one side, I will get a psi star box of del t square psi. So this minus 1 upon c square times del t square is coming from the box of psi's temporal part. And then the Laplacian part, which is hiding in the box, that will also have a psi star and psi. Similarly, the opposite way, this derivative over here, the box of psi star will give me minus 1 upon c square del t square of psi star, and the psi will be on the left, and there is a relative sign difference between the two terms, so here is a minus. So effectively you can see how these two brackets will emerge out, one for temporal derivative and one for spatial derivatives, and that should be equal to 0 because of the identity. Now you can see the quantity appearing over here is nothing but the tempo. So what first I can take? I can take the temporal derivative on the other side of equality. So both the terms should be equal to each other then. Then we can see that both the terms are actually the derivative of this quantity. The temporal part here is just the time derivative of this quantity, while the Laplacian part here is just the gradient of this particular scalar. So you can see that when you do the temporal derivative, a term like derivative of psi star and derivative of psi will also appear, but that will exactly cancel out from the term when the del t hits the second term here. So you will have only surviving terms as this, or even in gradient, if you work out, you will find out only surviving terms are this. So I can write down the equations which I have is the temporal derivative of this quantity should be equal to the gradient of that quantity. Alright, if that is the case, what I can do, I can just multiply iota h bar upon 2m c square on iota h bar upon 2m, because 1 over c square is already there in the temporal part. So I multiply this constant on the both sides of the equation. Then you'll see you can call this quantity as something. Okay, so let us call it some j0 upon so small j0, and so this times 1 power of c, let us say 1 power of c. So this constant 2mc. So with the definition of this, j0 is iota h bar 2mc square times this whole derivative is j0, and iota h bar by 2m with the whole thing as this as j. Then you can write down this equation is nothing but del mu del t j0 is equal to the Laplacian of the gradient of divergence of this. Okay, I should have been careful. I kept calling repeatedly at gradient. This is the divergence of this, because this is a vector. Gradient of a scalar is here, multiplying another scalar is giving me a vector. So this should be a divergence, not a gradient. So just correct your notes. This should be a divergence. Okay, and del t upon this should be divergence of this quantity. So therefore, when I define this, the first quantity is the temporal derivative of j0, and the second quantity is the divergence of the vector j. Together, so you can write down it is del t of j0 minus divergence of j is 0, which in the compact notation can be written like this: del mu j mu is equal to 0. Okay, so del mu j mu, as if you remember, is just the structure that it is eta mu nu del mu and j nu, and it is a diagonal matrix. Eta 0 0 is -1, so that's why relative sign difference between these two terms will come, and eta ii's are just spatial derivatives of vector j. So this is how you will get things. So in this, in order to obtain the continuity equation, the same equation or like this was coming in the Schrodinger equation as well. Now the lesson we have learned that we have to modify the definition of j0 to this much and j to this. J looks untouched. The vector j was the same definition which you used to get in the Schrodinger picture. However, the j0 has changed. In j0, this was just psi mod square. So therefore, this was called probability density previously. This time, I have to call psi mod, not psi mod square, but psi star del t psi minus psi del t psi star with a iota h bar 2mc square as probability density. Now there is a apparent problem with this. First of all, it is a real quantity because this and these are complex conjugate of each other. Therefore, this iota multiplication makes it real. This is fine. However, the requirement of the probability density is not very acceptable solution. Okay, why do I say so? Because if I just look for stationary solutions, I know there are positive energy solutions or negative energy solutions. So let us cook up a generic solution which will be a superposition of a probability in positive energy solution and negative energy solution. So this is a positive energy solution of Klein-Gordon. This is a negative energy solution of Klein-Gordon. So then I can do the superposition with coefficient psi plus and psi minus. That is also a valid solution for the Klein-Gordon equation. Then I take the first derivative of psi, which will give you this quantity. This is simple algebra, you should follow up. Then I calculate the psi star del t psi. There is a bit of algebra. You have to take the psi star, which is the complex conjugate of the psi, and the derivative of psi, which we have just evaluated, make the product. Then you will get various terms. There will be psi plus mod square of this, mod square of that, but then there will be cross terms, which will be like this. The cross terms will be like this. That is just simple plain algebra you have to verify. And then you have to take, in order to get the probability density, you have to take the complex conjugate of that, subtract those things out, multiply with iota times something. So that's what let us do. So I take this quantity, which is obtainable over here, and this quantity, which is also obtainable over here. And when I do the subtraction, the crucial thing is that the cross term, if you see, are exactly the same, they will cancel out. But there is a relative sign difference between the psi mod square terms. So this is iota I E h bar and this is minus iota I E h bar. So when I compute this quantity, the cross term will vanish, cancel each other, but the mod square terms will survive with a sign difference, because there is a sign difference between these two. That means the probability density will survive with a sign difference. So therefore, there is a problem at hand, because the definition of probability density is coming with A minus B kind of structure, and this is not always necessarily positive semi-definite. Remember, whenever psi plus is greater than psi minus, it is positive. But if I am looking for a generic solution, there is no guarantee that psi plus has to always be greater than psi minus. Even a psi minus, which is, let us say, 3 by 4, and psi plus, which is 1 by 4, so or something, some number which is making the normalization to 1. So let us say this is root 3 by 2 and it is 1 by 2. In that case, psi minus is greater than psi plus. It is a valid solution of the wave equation, but for that it turns out the probability density will become negative. So this will become 1 by 4 and this will become 3 by 4, and probability density will become minus 1/2 of h bar E upon m naught c square. So therefore, whenever psi plus mod square is greater than psi minus mod square, you have a problem at hand. You will get a negative probability density, which is not acceptable. For one particular case, if suppose I just look at the negative energy solution, which is this, its probability density is completely negative. So if we have to keep the continuity equation, J0, which can be negative now, cannot be interpreted as probability density, because it can be, probability density of any distribution should be positive semi-definite. So there was a problem as far as initial Klein-Gordon equations were discussed. The probability density's replacement in the relativistic limit was not clear. Psi mod square, which was being declared as probability density, is not a protected quantity. Remember, in the Schrodinger equation, we had this structure that del t psi mod square was equal to minus of divergence of J. And then if I integrate it over all space, then since this will take things on the boundary of, this is Gauss divergence theorem, divergence of a vector over all volume is equal to the vector dot the area element at the boundary of the volume, that is up to, if I am talking about whole universe, it is up to infinity I have to go. That means I have to do the surface integral on infinity, and wave function are falling faster to infinity, J vanishes, so the right hand side vanishes. So that means del t up of d3x psi mod square is 0. That means total probability in all universe is a conserved quantity in time. So this is full volume, this is probability density, and total integration is total probability of finding a particle in all universe. That does not change in time, that remains protected. So that was a feature of Schrodinger equation. If I want to do the similar kind of thing, what is protected? Again, J0 will be protected. So if you same thing you do, psi mod square will be written like psi star del t psi minus psi del t psi star. but the algebra will turn out to be the same. So this quantity integrated over all universe will be a protected quantity in the Klein-Gordon domain. But this is not a positive semi-definite quantity. So I do not know what is the replacement of the probability density then, and what this quantity is telling us, which is J0. So one idea was either multiply J0 with some charge and start calling things as charge density, which can be positive or negative. Or you do not go as far as taking the wave functions directly as the solutions. They have to be replaced by certain operators in order for them to act on wave state and give you the probability densities and whatnot. And that approach where the solutions, we fed in the solution into the probability density equation, that is not allowed if in one school of thought. That suggests that psi is not a known solution, should not be a known solution, better they should be in operators. And that will give me an operator at all x n times. Psi is a function of x n times. That will take us to quantum field theoretic domain, which we will do in the coming weeks. But this is one proposal, that there is no good replacement of probability density in Klein-Gordon level. I should not use the J0, which is obtained by continuity equation, as a probability, but rather think carefully whether it should be some charge density, or maybe it is operator, quantum field theory, or maybe we can try to replace the Klein-Gordon equation with a better relativistic equation. So the problem, as we saw, came about from the negative sign of E, and negative sign of E was coming precisely because E square was something else, and which was coming from the double derivative structure of del T. That gave me E square kind of equation. If we have single derivative equation, probably then we will be safe and we will be getting a correct energy density and other things. That is the domain of Dirac equation, which we will do in the next class.